Hi, in this lesson, we'll talk about what it takes to develop a program. You may refer to chapter 5.1 of the textbook for more information. On our last season of Python 3 programming, we learned to control the flow of our program using if-else statements as well as loops. We then learned how to write user-defined functions to make use of patterns to reduce repetitiveness in our code. Finally, we learned more about the 4 data types and the functions related to them: integers and floating points, lists, as well as strings. But it takes more than just a piece of code to make a good program and solve certain problems or cater to your client's needs. So by the end of this lesson, you'll understand the importance of proper planning in developing a program. In particular, developing the right test cases will contribute to the robustness of the program. Thus, we ask ourselves, can we design the right test cases, and how do we do so? What else do we need to develop a good program? Is it all trial and error and luck, or is there a method in the madness? By the end of the lesson, you will learn how to describe and understand all these 5 stages of developing a program. So let's jump right into it. Generally speaking, these are the 5 stages that you need to develop a program. We first receive the problem and gather information on how to develop it. With this information, we plan how we want the program to look like before we write out our code. After coding, we need to test and refine the program to see if it fulfills the requirements set out in stage 1. Finally, we roll out or deploy the code to solve the problem it was developed for. Does this sound familiar to you? After all, it is similar to the software development lifecycle or waterfall method you may have seen before. The SDLC has 7 stages, but if you look closely, it follows the same pattern as our 5 stages. Now let's go through the details of each stage. In stage 1, we ask ourselves, what is the exact problem we're trying to solve? Some examples of things that should be done in stage 1 are interviewing the intended audience of the program, as well as specifying the inputs as well as the outputs of the program. It is important to specify in as much detail as possible so that when we write our code, we do not have to ponder how we want the inputs to look like or how the outputs should look like. Let's try it out with an example. Say we are trying to write a program that determines if a given year is a leap year. To understand the nature of the problem, we must first ask ourselves, what is a leap year? How do we tell if a year is a leap year? For this, we may need to ask around to find out. Here, I decided to ask Google to help me to define a leap year. The second question we ask is why the program is needed. Will the program make our lives easier? Will it be useful? Well, sometimes the answer to this question is because my teacher said so, in which efficiency and usefulness may not matter anymore. The answer to why you need a program is yes. Finally, we identify what the program is expected to do. What are the inputs and outputs to this program? Recall how we define a problem in chapter 2 by specifying the inputs and the outputs, including its data type as well as the expected values for the output. For this problem, the year is our only input, and the result should tell us if the year is leap or not leap. It's now your turn to try with an example. We have briefly discussed this question in class before. Pause the video now and see if you can successfully write down the requirements of this code to turn a number or round a number off to 3 significant figures. Well done. Here are some sample answers. Stage 2 is to plan our solution. In this stage, we try to come up with an algorithm to solve the problem. Can we apply our algorithmic thinking techniques, such as breaking the problem down to smaller parts, identifying patterns, or generalizing the problem for use in various similar problems? When you have a rough plan, you should sketch it out as a flowchart or pseudocode to help you firm up your thoughts and communicate them with others. Now we can write our code. Here's the code we have written for you, translated from our flowchart. But it looks like there are too many nested if-else statements. Can we simplify the code using Boolean operators, not, and or, to use just one if-else statement? Pause the video now to try it. We're not done yet. We need to test our code to make sure it works, and refine it to iron out the bugs and errors. So we test it against a few test cases to see if our code gives us the answer we expect. Here we use 2020 as our first test case. We know that 2020 is a leap year as it is divisible by 4 and not by 100. And indeed, our code tells us that it is a leap year. Great! Our next test case is 2000, and that's also a leap year according to our rules. This test case passes too, as our code correctly identifies it as a leap year. It's not enough to just test our code on leap years. We also need to make sure that it can identify non-leap years. So we use the year 2900, which is divisible by 4 and by 100, but not by 400. So we know that it is not a leap year. Indeed, our code classifies it as not a leap year. Pause the video now and think. What other test cases should we test our code with? What other inputs can we preempt that our users might use? Here's a possible test case. Users might end up spelling the year 1984 or something similar, which will break our code as it is not designed to handle such input. As a developer, we have a decision to make. Do you want to accept this as valid input? If so, how do we convert this to an integer that our code can process? Otherwise, how can we reject this input? Here's a typical way to reject such inputs. We use an if statement to check if the input year consists entirely of digits. If so, we typecast it as an integer, else we tell the user that it is not a valid year. This code is put into a while loop, which will keep asking for inputs and re-inputs until the year is valid and the break statement is reached. Once the while loop is broken, we can then go on to the process section of the code to identify if the year is leap or not. Those of you who are familiar with the syntax of try except, you may also choose to use that to handle exception cases that cannot be typecasted as integers. This is a process known as data validation, which you will learn more about in Chapter 6. At this point, you may be wondering, how did we come up with our test cases? There's an art to it. We usually design test cases to cover 3 scenarios or conditions. First, we have the normal conditions, where the input is exactly how we expect it to be. We have 2 kinds of outputs in this code, so we should have a variety of test cases to cover both leap year and non-leap year outcomes, to ensure our code can handle both and give an accurate output. The first 3 test cases we had earlier, 2020, 2000, and 2900, are all test cases for the normal conditions. On the other end of the spectrum, we have error conditions, which are inputs that we want to reject. The program should be able to reject these inputs and potentially ask users to re-input the data. In our previous example, we rejected 1984 spelled out in full and asked for re-input. Finally, we have the boundary conditions, which are the limits of what the program is designed to handle. Your code should still be able to accept and process them, but they are extreme cases. These are a little tricky to design, as sometimes there aren't any boundary conditions. For example, think of what is the range of values that we expect our code to work. What is the smallest here? Is there a biggest? Each of these conditions should have test cases to see if our program can handle them well. Examples of each condition, as well as the test cases, are shown in our leap year code. Here we have chosen 1 as our extreme data because 1 is the smallest possible year, AD. And because we do not know when the world will end, we do not predict a biggest year. Finally, when we are satisfied with our code, it's time to roll it out for our users to use. Some of the events that take place during this stage are training users to use the program. If there's an older code in place, we must make sure that users are able to handle the changes. And so we need to transition from an old program to a new one. If a code is just one part of a bigger program, you also need to ensure that it fits seamlessly so that the inputs and outputs can flow seamlessly from and to other parts of the code. Hence, the need for transition. We should also gather feedback from users about the effectiveness of the program and consider if we need to make any changes that can improve usability or effectiveness. In summary, these are the 5 stages of developing a program again. But do programmers really go smoothly from stage 1 to stage 5 and end there? Well, nah. We have spoken before about agile software development, where we go through the stages in iterative loops. Hence, each time we do more planning, more coding, and more testing based on users' feedback on the last version. Sometimes to speed up the progress, we may even need to gather requirements while writing and refining the code. This is closer to the reality of program development. In conclusion, I'll leave you with this flowchart meme. How do you write a good piece of code? Well, no one really knows. Program development is messy progress. And if you find yourself constantly writing and rewriting, refining, testing, and planning again, then you know you are doing it right.